First of all, thank you for having me. And well, it's nice that I could be here, although I'm not really there. But it's nice that I could still be there virtually. And well, I can still see you on the live stream, so that's nice. So in this presentation, I'll be talking about a new type of timing attacks called timeless timing attacks. But before I go into all the details, I'll try to give some background on what timing attacks are. So if you have like this piece of code, for instance, this is vulnerable to timing attacks. So if there's like a secret condition, and if that's true, then there will be a longer operation, and if it's false, it will be a shorter operation. So to make it a bit more concrete, we can look at the string comparison of the word passion and password. So we just use this string compare. So what this string compare does, it will first check the first letter, because it can only check one letter at a time. And then it will check if the P equals to a P, which is true. And then it will move on to the next operation, which or the next character to check. And well, because it's not returning something, it will be a longer operation. So it will again check whether A equals A, which is true, and then move on to the S, and then to the second S, and then eventually it will come to the comparing the I with the W. Of course, these are not equal. And at this point, the string compare can say, well, I noticed that they're not equal, so I will return -1. So why does it matter that it does it like this, and how does this make it vulnerable to timing attacks? So if we look at the timeline, let's say that every checking one character takes like 100 nanoseconds. It actually takes a lot less, but just for the sake of argument, I will say that it's 100 nanoseconds. Then you can see that if the first character would already be incorrect, it would only take 100 nanoseconds, the whole operation. So then you can try like every possible character, and then if one matches, then you know, okay, it must be this one, because then it will take 200 nanoseconds, because it also needs to compare the second character. So that allows you to go like character by character, and then you can figure out character by character what the actual password is. So this is kind of the general concept of how a timing attack works. This is like on a local system that you can do this, but as an attacker, we are often also interested to perform timing attacks against servers. So what we do there is then, as an attacker, we send a request to the server, and then the server will process this and then send a response back. So this looks a bit like this. So here we can see that it took 3 seconds and 27 milliseconds. And well, from this we know we can infer some things, but usually we want to have like quite a lot of different measurements. So we, and receiving it is, we can filter it out by using some statistical analysis on all the observations. So for instance, we do another request, and then you can see that it was hanging a bit in the third node of this path to the server. And as a result, now the request took a bit longer to process at the server. So here it was 4 seconds, 48 milliseconds. So it can, well, like there is quite a bit of variation, and that's why an attacker would need to obtain a lot of different measurements, especially when the difference, like if he wants to well, determine the difference in timing between two requests, it will, and this difference is quite small, then a lot of requests are needed. So this is like the classical way of performing time attacks, which is sequential timing attack, because you send requests sequentially, so one by one. And well, here the measurements are affected by jitter on all the sub-operations. And well, these sub-operations include the network path, so the path over the internet from the attacker to the server, then the jitter of the processing time at the server, and then also the network path back from the server to the attacker. And there might be some other aspects that may also introduce some jitter. But in most cases, the main source of the jitter is from the network path. So this means that, well, if it's over a long distance connection, then, well, there will be more jitter, which means that the attacker will need more requests. So a solution for the attacker could be to, well, launch an attack from a server that is physically close to the targeted server. But in certain attack scenarios, like cross-site attacks, which I will talk about later, well, the network is not under the control of the attacker. So the attacker cannot choose where to send the request from. So this makes it a lot more difficult to well, execute the attacks. So we did some experiments to see how many requests we actually need. So we had 2 requests, so a baseline request and then a request that took well, a certain amount of time extra, and distance and 5 microseconds. And then we looked at, well, based on requests sent from our university, which is in Belgium. We looked at how many requests we need to differentiate 2 requests. And so, for instance, for a timing difference of 50 microseconds, and the target server is also in the EU, then it took 333 requests to be 95% sure that we have the correct result. For a smaller timing difference, for instance 20 microseconds, it took 2,926 requests on average. And then the smaller bits, so for 10 microseconds, it's 20,000 separately determine this timing difference with this classical type of timing. And then we can also see that the further away the connection is, or the more network paths it needs to traverse, the more requests you need to achieve the same performance of the attack. So, yeah, for instance, the 50 microseconds for the US, it's more than, well, almost 4,500 requests. And then Asia, I think it was a server in Singapore, there we needed more than 7,000 requests to determine this timing difference. So, well, this is the case today. Like, if you would perform a time attack, this is, well, what you would achieve. So that would be kind of the maximum performance that you could get. So then we were taking, like, maybe there are some other ways that we could perform timing attacks. And that's when we thought of this idea of a timeless timing attack. So we made the observation that using the absolute time is quite unreliable because it will always include the jitter for every request. So if you're comparing two requests, it will have like jitter from both requests. So that's not ideal. So we didn't want to rely on time anymore. So that's why we call the attacks timeless. And then instead of relying on this sequential timing measurements, we make use of concurrency, and we only consider the order in which the responses are sent. So this means that we don't use any absolute timing measurements anymore. And also a very strong benefit of these attacks is that they are completely unaffected by any jitter on the network. So I'll show how this works exactly at the end of the same example. So now instead of this one request, we send two requests at the same time. So these two pink ones. And we make sure that they're in a single packet that is sent to the server. So then we can see they're sent at the same time, and they also arrive at the same time at the server, where they're processed in parallel, and then they're sent back, well, depending on which one finished first. And then we can see, as the attacker, we can observe that the first, well, this light blue one arrived first at the server. And as you can see, we don't use any timing measurements. We just use the, well, the relative order in which the responses were returned. So we have again the same example where there is some delay on the network, but as you can see, because both requests are in a single packet, they still arrive at the server at the same time. And then again, they will be processed concurrently, and then the light blue one processed faster, which means that well, we as an attacker can learn something from this. So there's a few requirements to perform this type of timeless timing attacks. The first one is I think the most important one, and that is that the requests need to arrive at exactly the same time at the server. So if there is a delay, then both requests will incur the same delay. So, well, this means that they will still arrive at the same time at the server. And the requests also need to be processed concurrently, so in parallel, because if you would, well, process one after the other, then you don't, well, then the response order will be the same as the request order always. And that also brings me to the third requirement. So the order of the response, it should reflect the difference in execution time. So if the one request takes less time to execute, then it should be, well, the response of it should be sent first. So then we can see how we can achieve this. So the first requirement was that the requests need to arrive simultaneously at the server. And there we have two options, basically. The first option is to abuse multiplexing in the network protocol. So for instance, a big difference between HTTP1 and HTTP2 is that in HTTP2 you have multiplexing, which means that you can send multiple requests over one single connection, and then they will be processed in parallel. So we can also use this to put two frames into a single TCP packet. And yeah, in our experiments, we built a custom HTTP2 client, and then we used some socket options to make sure that both of the headers frames are in a single TCP packet. Another option is to use an intermediate network protocol, so one that encapsulates packets. So a good example for this is the Tor network, because it encapsulates the TCP traffic as Tor cells. And for Tor onion services, so these are the .onion addresses for Tor, there the Tor circuit is until the target server. So if we have packets from two different TCP streams, so we make two different TCP connections to the server, then we can still somehow make it that they will be merged into a single TCP packet. And then, well, because they're in a single TCP packet, they will still arrive simultaneously at the server. So this is how it looks like visually. So in the case of HTTP2 with multiplexing, we have our two headers frames, and we make that they are packed into a single TCP packet. And then for Tor, we have, well, it's for HTTP1 in this case. And there we have two different GET requests on two different TCP connections, and they're added to two different Tor cells, but the Tor cell is less than the well, maximum packet size of one TCP packet. So we can still make that they will be sent in a single TCP packet. And then they will still arrive simultaneously at the server. And then for the two other requirements, so on the one hand, we have the concurrent execution, and that's mainly application dependent. So I think for most web servers, requests will be executed in parallel, so that wouldn't be a problem. There are some exceptions to it. For instance, certain crypto operations, as you have in SSL and TLS, they will rely on sequential operations, and then with the current techniques, it's not possible to use the multiplexing. So it's a bit more tricky to execute the attack. And then the third requirement is that the response order should reflect the execution time. And that's also in most situations the case, because a response will be generated immediately after the processing has been finished. So then the attacker can infer this response order. And we wrote a paper about these attacks, and we explore defenses based on this requirement. So by trying to change the response order. But yeah, you can have a look at the paper if you're interested. So in our research, we considered three different types of attack scenarios. So the first one is the direct time attack. So there you have the attacker who's directly sending requests to a server. Then the second one is the cross-site timing attack, where the attacker has some malicious JavaScript payload on a website, and then the user visits this website, and then this malicious JavaScript will send requests to another website, and from this other website, it will try to extract sensitive information about the user. And then the third thing that we evaluated was the Wi-Fi authentication. This was mainly work done by my colleagues who are from the NYU in Abu Dhabi. So I'll dive a bit deeper into how the different attacks work and how we can execute it. The direct time attacks are quite straightforward. So we make an HTTP2 connection, we initiate it, then we send, well, we create 2 headers frames, and then we just write to the transport layer well, the data for these 2 different headers, and yeah, that makes it they will be packed into a single TCP packet, and then we just need to determine when the response of the different well, the order of the responses. That's all we have to determine. So I created a small framework for this, which is available on this GitHub link, so you can try it out. And it's fairly simple. So you determine the 2 different requests that you want to make, and then you call this H2 time, which is the module that I made, and then you can run the attack and get the results from it. So it's quite straightforward there. So I definitely advise you to take a look and if you want to try it out. But maybe it wouldn't be such a good idea to try that on my website, but try that on your own website maybe. Okay, so that brings me to the second attack scenario, so the cross-site time attacks with the malicious JavaScript. So as I said, the victim will visit the attacker website, or at least the website with JavaScript from the attacker. But the big difference between this attack scenario versus the other one is that the attacker does not control the network connection of the victim. So this means that it's not possible to just merge 2 requests by manipulating the sockets, or by running like sending raw requests. We always need to send a request through the browser, and that's why we need a new approach. So what we can actually do is to leverage the TCP congestion windows. And I'll explain in a bit how that would work. So this congestion window is a sort of mechanism that is in the specs of TCP, and it dictates that a client can only send a limited number of packets at once, and then all the following packets will be queued. And then once the acknowledgements arrive, the next packets can be sent as well. So here the attack still looks relatively straightforward. So what we first do is we first make a large post request, which will fill up the buffer of this TCP window, and then we send 2 different requests to the 2 different URLs that we're interested in, and then we just determine which one responds first. And then I'll now try to explain what kind of effect it has and why it actually works. So on the left-hand side we have the browser, and then the browser is sending requests according to this example to the server or to the website on the right. So it will first send this large post request, which is made up of several TCP packets. So it's more than one TCP window. So yeah, let's say, for instance, that it's something like 20 kilobytes. So then the browser will first schedule this first TCP packet, then the second one, and then all the rest until it reaches this TCP congestion window. And everything that's after this TCP congestion window, it cannot be sent yet. Yeah, this window is typically 10 TCP packets, and all the rest that comes after it needs to wait. So it will be queued. But at the same time, the browser or the attacker can still send requests. So, for instance, the GET requests for this URL1, and because the kernel still needs to wait before sending the rest of these TCP packets, it will just add it to the queue. And then when the attacker sends the request for the second URL, it will add it to the same TCP packet, because that would be the optimal way to send small TCP packets. So because these things are being queued, this means that they will eventually end up in the same TCP packet. And only when the web server sends an acknowledgement to the victim or to the client, then the rest of the packets will be sent. So then they will be removed from the queue and sent to the server. And as you can see here, the URL1 and URL2 will be in the same TCP packet, so they will arrive at the same time at the server. And that brings me to the third attack scenario, so where we try to attack the Wi-Fi authentication. So we performed a time attack against AAP PWD, which is a quite popular authentication mechanism for Wi-Fi. And people already knew that there was a timing leak in this the handshake mechanism there, but because the timing difference was so small, they thought that it was not possible to exploit it. So the timing leak was there because they they didn't have a constant time implementation. And with these timeless timing attacks, we managed to still exploit this vulnerability. So again, we had to achieve this simultaneous arrival of the two requests. And we did that by encapsulating the two PWD ID messages in a single AMPDU frame. So I'm not an expert on Wi-Fi, so this is something that mainly my colleagues were doing. But it's something that doesn't require too much effort. Well, it required quite some effort to make it work, but now that we have it working, it's not too much effort to try this yourself. So the exact details of this attack are in our paper, so you can have a look if you're interested. So the timing information that was leaked, so that was the number of hash-to-curve operations. This can be abused to launch a dictionary or a password brute force attack. And then we try to evaluate how well it would work. So we used the RockU dictionary, which is a password list of 40 million passwords. And then we managed to exploit the vulnerability in 86% of the cases. And fortunately, well, we reported these issues, and I think in most systems they have already applied a patch for it. So we can thank the Wi-Fi people. So this was, these were the three different type of attack scenarios that we considered. So what we now want to know is, we introduced these timeless timing attacks, but are they bigger, better, stronger than these other sequential timing attacks that we've known for many, many different years, many years before? So again, we did some experimentations to figure out, how well it performed. So we have the same table as before, so with the EU, US, and Asia. So these are the same numbers as before. But we then also tried to see how many requests we need when we perform an attack on the same local area network, or even from the local host. And this is with the sequential time index that we've known for many different years. And then we tried the same thing with the timeless time index. And then, as you can see, these timeless time index, they work, well, in some cases slightly better than the attacks performed on the local host. But, well, the most important thing is that these timeless time attacks, they can be performed from anywhere on the internet. So any server that is publicly accessible, and for instance runs HTTP2, can be attacked with these timeless time attacks. So if we want to measure a difference of 50 microseconds, we only need 6 requests to know this with a certainty of 95%. And we can even go as well, a timing difference as small as 100 nanoseconds. So that's even a bit better than the attacks performed over the local area network or on a local host. And well, if you think about it, it actually makes sense because the main thing that causes some performance degradation in these timeless time attacks is the jitter of the execution. And because these timeless time attacks are immune, let's say, from the jitter occurred on the network. So then it doesn't actually matter from where we send the request. So then the best one would be local hosts, and as you can see, the performance is somewhat similar. So now that we know that, these attacks are quite bad, we also wanted to explore what we can do to defend against it. And there we have, quite a bit of different options. So the first option is a very classical one, or a classical type of defense against time attacks, and that is to ensure that every operation takes the same amount of time. So we have a constant time execution of our algorithm or something. So this is a quite good strategy for crypto operations because there we have one input, then a certain algorithm, and then an output. So if we then just can make this algorithm constant time, well, it's not easy, but it is feasible in most cases. So then we make sure that there are no timing leaks. But if we have, for instance, very complex applications, and I would say that most web applications are like this, so we don't have just a single algorithm, but we make use of many different third-party applications, such as a database or a backend API, all kind of these things. There, I think it's very, very difficult to have a constant time execution. So that's not really an ideal strategy. Then another option, so option 2, is to add some delay to the requests, because, this would kind of simulate the jitter that you would observe on the network path. So in our paper, we actually evaluated what would be the overhead of this. So we used a big data set called HP archive, and then we would estimate what would we actually have to do in order to make the performance of the time attack the same as this sequential time attack. But well, unfortunately, what we saw is that the overhead is well, can become quite high. So it could be several milliseconds on a single request. And then you would have to do it on every request. So this means that just to protect against these time attacks, you would have to, well, delay many requests. So I think this is also not really a very optimal solution. Then a third option would be to disable the concurrent execution, so that you don't have any parallelism anymore. But unfortunately, well, it will also have a very big impact on the performance of your application. So the main difference between HP1 and HP2 is that in HP1 you have the head of line blocking, which makes it if you send one request and then another one, then the second one can only start to be executed as soon as the first one has finished execution. And in HP2, you don't have this limitation anymore, and they can be executed in parallel. So if you would, well, disable this parallel execution, then you would lose the performance benefits from having HP2, which I think can be quite large. And then we can also try to look at defenses that are more specific to different attack scenarios. So for instance, with the cross-site attacks, more options are possible for the defenses because the attacker has less control over the network and how requests are sent. So one option would be not to send a cookie with the request. And well, fortunately, I think recently, Chrome has made the same site attribute on cookies the default. So this means that now, I think only since somewhere in August, when you or when a site does not change anything to the defaults, then if you have a cross-site request, then this request will not have a cookie. But of course, it's only on Chrome, so all the other browsers, you would still be vulnerable. So the reason why this is a very effective approach is if there is no cookie, then, well, on the request, there will be no authentication of the victim. And because there's no authentication, there's nothing user-specific that can be leaked in this request or response. So this is, I believe, one of the most elegant solutions. Another option, so option 5, is to only send a single request per TCP packet. So, well, because one thing that we had to abuse was to make sure that we had 2 requests in a single TCP packet, because then they arrive at the same time at the server. And if it's not the case, then the request triggered by the attacker will have different delays, and then, well, the attack will, well, it might still work, but the performance will be very, very bad. So this means that the attacker will need a lot of different measurements, and then, well, it might not be possible to get them in time. So one possible well, downside of this defense is that there will be some bandwidth overhead, because the requests are, well, the HTTP requests are rather small, so the client can benefit quite a lot by putting them in the same TCP packet. And then there are some other well, one last option, and that's for the encapsulation protocols, and it works a bit similar to the previous option, and it is to make sure that we don't we don't encapsulate two different TCP, what was previously two different TCP packets into a single TCP packet after encapsulation. Because, well, if the packets are not joined in a single TCP packet, then they will also not arrive at the same time at the server, and then, well, it's not possible to perform these timeless timing attacks. So this is something that, for instance, could be possible in Tor or in VPN, which also is an encapsulation protocol, or there might be some other protocols as well. So I'd like to also briefly say that we're still working on this, and that, well, we have several things planned for future work. So in our analysis we did, well, we only considered a limited amount of network protocols. So I believe that it will still be quite interesting to also test whether other protocols can be also exploited to perform these concurrency-based or timeless timing attacks. And, well, we also want to, so on the one hand, we want to look for protocols that enable this multiplexing, which is, for instance, the case with HTTP2. So I believe that most likely HTTP3 will also be vulnerable, but we still have to look into the details of how that would work. And then we also want to look at protocols that might encapsulate different packets. So in our case, we looked at Tor, which we found could be abused, but some other options might be VPN or some other lower layer protocols that are, well, optimizing for the performance of these network protocols. And then finally, we also want to see if there might be other techniques to coalesce different packets into a single TCP packet by abusing something like buffers or something. But that's still something that we need to explore. So that brings me to the conclusion. Well, in this work, we explored concurrency-based timing attacks, which we also call timeless timing attacks. And we found that they're not affected by network jitter at all. So this makes it possible to perform remote timing attacks that have an accuracy or performance that is similar to the case where the attacker is on the local system and is trying to attack a service from the local system. The attacks can be launched well, against either protocols that enable multiplexing or by using a transport protocol that uses encapsulation. So multiplexing is, for instance, the case with HTTP2, and encapsulation is the case with Tor. So all protocols that match the three requirements that we determined might be susceptible to these timeless timing attacks. And we created practical attacks against HTTP2, then the Wi-Fi handshake, EAP-PWD, and also HTTP 1.1 over Tor. And then as future work, we also want to perform a more extensive evaluation of the different network protocols and see if they're vulnerable to these type of attacks. So this concludes the presentation. If you have any questions, I would be happy to answer them here. But if you have, well, if you later have something that you would like to ask, you can contact me on Twitter or via email as well.
So, any questions? Ребята, есть вопросы? So, no questions for now. Thank you, Tom. Thank you so much for your report. Applause, guys. Аплодисменты, пожалуйста. Thank you. Hope to see you next year, Tom. Bye.
Thank you.